Right, so you're probably wondering, what is a primordial black hole, and why are we looking for them? Well, let's start with the second part, the black hole part. A lot of people think of black holes sort of like giant cosmic vacuum cleaners. They just sit out in space and suck up anything that happens to get too close, whether that's a planet or Matthew McConaughey. But black holes don't have to be giant. In fact, the key to making a black hole isn't so much the mass as it is the density. So anything can become a black hole if you compress it enough. For instance, if you took the Earth and squished it down to the size of a marble, the Earth would turn into a black hole. But I want to go even further. So imagine taking the Empire State Building and crushing it down to the size of a proton. Now you might think if we took the Empire State Building and turned it into a black hole, it would swallow up the Earth and we would all die. But that's actually not what would happen. For one thing, the Empire State Building isn't really massive enough to exert a strong gravitational pull. I mean, when you walk past it on the street, you don't really feel much of a tug, right? So it wouldn't really suck up that much mass. In fact, it would emit more mass than it would suck in. And the reason is, really small black holes glow. They're not black. They glow in much the same way that a piece of iron would glow if you pulled it out of a really, really hot furnace. The difference is, the black hole is a lot brighter. So our proton-sized black hole would glow with the brightness of something like 10,000 Hiroshima-sized nuclear bombs going off every second. And this would take place over the course of many years until the black hole is just completely evaporated. So yeah, we would all still die, but it would at least be really exciting. Now, it's very difficult to form a black hole this small. I mean, how would you even go about compressing something that much? So the only time it ever could have happened is in the early universe, right after the Big Bang, because at that time, there was a lot of mass, but there wasn't a lot of space to go around, so things were already really dense. So we call them primordial black holes, because they formed out of the so-called primordial soup. And understanding how many primordial black holes are around today can help us understand the early universe better. So it's my job as an experimental physicist to look and try and find evidence of primordial black holes. And if we find them, how many are there? So how do we do it? Well, what I do is I look for the gamma rays that are emitted from that sort of long-lasting explosion that I talked about. But it's sort of a tricky problem, because if you see something in gamma rays, how do you know what it is? There's a lot of stuff in the sky that emits gamma rays. There's supernova remnants, there's quasars, blazars, there's stuff with funny names. So if you see something, how do we discriminate? So the key is we found that black holes would actually be expected to move a little bit in the sky. It's a lot like being out at night, looking up at the sky, and seeing a point of light and trying to tell, is that an airplane or is that a star? Well, the easiest way to tell is just to watch for a few minutes. And the airplane's going to move a little bit, but the star's going to stay put, right? And I want to do the exact same thing, only with gamma rays instead of visible light. So I developed an algorithm that can look at a gamma ray point source and determine whether it's completely stationary or whether it's moving very, very subtly. So when we looked, we didn't find anything that was moving. I think everything was completely stationary. So we didn't find any primordial black holes. That means the best we can do is put an upper bound on the total number that we see. The good news for you is you can rest easy each night knowing that you're safe from the threat of primordial black holes.